So my name is Peter Dunne. I'm an Irish scientist living and working in France, and my background is in magnetism and electrochemistry, and now I work primarily on rare earth separation. So there are 15 rare earth elements which are from lanthanum all the way to lutetium. So that sits at the very bottom of the periodic table. And as well as those 15, there are another two, scandium and yttrium, which are chemically similar and considered part of that same family. And then we divide them into the heavy rare earths, which is from gadolinium upwards, maybe, or europium upwards, and then the rest are the lights. We actually use rare earth elements a lot more than people realize. The most important use for them is in magnets, which we use either in motors, for example for cars, but also, for example, in turbines. So wind turbines, it's extremely important to have a way to convert, let's say, mechanical energy into electrical energy that we can then store. We also use them, for example, for polishing glasses. So, for example, any of your lenses, we also use rare earths for this. And they're also very important as catalysts for certain types of petrochemical reactions. But the most important, particularly for the green transition, are magnets. Excellent question. No, rare earth elements are not rare. They're actually a lot more abundant than, for example, silver or gold. But in fact, they're just very dispersed in the Earth's crust, and there are very few places where they concentrate sufficiently that they can be economically mined. That's just for historical reasons that they're called rare earths. The major issue is to separate the rare earths, because notoriously the rare earth elements are very similar to each other chemically. So that means that to actually separate them requires a lot more effort and time compared to other elements. And typically at the level of industry, what we use is a technique called solvent extraction. So that means we take a water-based acid, we dissolve the rare earth elements inside, and we mix that with an organic solvent like kerosene. And we mix that. One out of all the 17 will preferentially transfer into the organic solvent, and we repeat this many times until we separate element by element, or we do them a few at a time and then do a tree of gradually separating one from the other. So this is quite time consuming. It's also very heavy in terms of chemical needs, and it can be polluting if it's not done carefully. So this is chemically very heavy technique to use. It's very intense, but it's also, at an industrial scale, it has been the most economically viable one. But then there are major issues with having to deal with waste treatment, and then the fact that it also, if people want to reduce their carbon footprint, the fact that we use kerosene, which ultimately comes from petroleum, this of course is another issue. So the thing about the rare earth elements is chemically they're very similar, but magnetically they're very different. So what we do is we avoid organic solvents like in solvent extraction. Instead we use a water-based system. We put inside an electrochemical cell, and what we do is use magnetic fields to concentrate the most magnetic elements at the electrode surface, and then with electric current transform them into a powder that we can recuperate. The benefit of that is we can actually have lower running costs and lower capital investment costs, and we can do this with fewer steps, which means we can also produce pure powders much faster than with other techniques. And the other key point is we target the most valuable and most needed rare earth elements. So that means dysprosium and neodymium in particular, which we need for magnets, which is what the energy transition is really depending on for both electric vehicles and wind turbines. So our main focus is trying to get these either separating them from recycling, so recycled magnets, production losses, or also to work with mining companies to help them valorize and improve the value of their products with, let's say, in a cleaner process with a smaller carbon footprint. Unlike AI or IT startups, chemical companies or industrial startups need a lot more capital investment to be able to develop their proof of concepts, their demonstrators and the pilot lines, because these cost a lot more money, so we need much more support to bring us to the level where we can actually demonstrate economically for all the partners in the world that we actually have a product that is convincing and usable and will solve their problems. Raw materials are the absolute foundation of our civilization. We need them absolutely everywhere. People actually who work in, for example, mining, who work in raw materials, they actually, believe it or not, they love the planet. They're actually, some of them can be extremely green, so people can have a very negative view of some of these industries. But there's been an enormous cultural change, an enormous push to try to make all these industries and raw materials as green and sustainable as possible. So the more people we can have in with fresh ideas and enthusiasm to really transform this into a totally green industry, this will make such a difference, not just for in our lifetime, but also for your children's lifetime too. So it's really a long-term thing to try to improve this critical industry, which we need. We've needed it for all of our civilization, and we will continue to need it in the future.